Yeah, welcome, and I'm happy about two things. For once, I think it's super that with our offering we are able to make a test system like the one just shown. So far, I've known it only from slides, but seeing the real pictures makes me very enthusiastic. And then secondly, I'm very happy that so many of you have stayed on until the last presentation. So my topic is conformance testing of automotive Ethernet networks. We haven't heard much about that today, but it is increasingly playing a role. So let's try to take a look inside the vehicle. The EE architecture is really changing rather strongly based upon several drivers, one thing being connectivity, then e-mobility, software over the air. Those are drivers which have the effect that the vehicle architecture is changing. And what we are experiencing now is more or less vehicle architectures that look like this or in a similar way for almost all of the OEMs. Unlike in the past, it's a real straight-lined then distribution and organization. And I will also have to try and find the pointer here, which doesn't get started. I don't know where to press. Here it is. So it gets started with one or few central and very high-performing gateways, then domain controllers with the known domains, powertrain, chassis, body, others, infotainment. They are managed by those domain controllers, and on that level you will essentially find Ethernet connections, partly also in domains like infotainment or others. There will be more and more Ethernet connectivity, and that is needed, and it's a motivation to also take a look at how you can test that. So if we take a look at conventional or classical bus systems, those of course continue to exist. This is a partial extract from the EE architecture. If you remember CAN Flex Lin, then testing can be done directly in comparison by providing for a line with the bus and connecting the network interface. The network interface is basically another bus participant seeing all of the bus communication, and it can be directly used as a test device. For Ethernet, it really is a bit different. Otherwise, I would be at the end of my presentation already, which is not the case. So I would like to take a look together with you, what does Automotive Ethernet stand for? Why is it different? Where is it different? What are the specific needs for testing? What are the solutions already available? And there specifically, what does the Open Alliance offer, a special interest group? And then a proposal that we can offer for a test system, that's one part. And then the hotly promised outlook onto the VT system. Of course, I want to offer that once again this year in my last part. Let's take a look at Ethernet networks. The basic difference that Ethernet is that it's not a bus system like CAN along the lines of all participants being connected to the same bus and seeing all the communication, but practically between all network participants. In the rule, it's ECEs, there are point-to-point connections, and in each case they are served with a separate PHY. So the communication will be interrupted time and again if you've got a switch like shown in the case in the middle, and that's a basic difference. It's not a bus like CAN, LIN or FlexRay, but it's really a point-to-point connection between various participants. So that's one given thing. Then as a rule for Automotive Ethernet we've got full duplex data transmission. So a mere direct line couldn't assign where the package comes from the left, from the right, because frequently then we've got more than two signal states. At 100 base T1, for example, there is a three-stage signal, and so much technology exchange that doesn't allow to identify where the packet comes from. And then finally, each link in the network requires one PHY, has to serve one PHY. So those are basic differences between Ethernet networks and classical bus systems, and they require accordingly adapted test solutions. If we take the subsystem Ethernet out, this has been the part of the vehicle architecture part that is already running with Ethernet, then it looks as follows. And I'll jump back a little bit. So if we want to take a look at the Ethernet network, let's take an example. You've got a LiDAR sensor producing data, and it wants to send them to the body in one way or another. So maybe the vehicle is expected to brake, start an emergency brake. Then it has to send the information to the domain controller, which is the first Ethernet participant. Then via the central gateway, they normally have got switch functionality, then to the domain controller, and then through the chassis bus to the appropriate ECU. In Ethernet terms, these are various link connections, and if you want to test them, then depending on the test requirement, so you have to get connected to each of the link connections. So you have to break up each link and guide them into the interface, and then the partial links you have to make it able to get enabled to see all of them. We take that test access points, taps, for each link of interest that you wish to study along the line. You will have to make available such a tap test access point. In the interfaces, there are two stages. There is one link being shown by way of an example between two link partners. So either on the file level, you can establish a so-called tap, or then on the MAC level, behind the file or behind the MAC. That has got different reasons, different reasoning. If you make the short circuit rather easily and quickly behind the PHY, then we've got short latencies. You have to imagine, even in test operation, the entire network has to be running. So data throughput through the individual partner has to be performant enough to avoid the entire network from collapsing. And nevertheless, we either have to analyze it, or then we have to also inject fault data. And for that, there are two levels: monitoring tap through a bridge directly on the PHY, or stimulating tap behind the MAC. So on the software level, where you can not only analyze, but where falsified test data or lapses or whatever can be injected and fed into the running and ongoing communication. Those are given things and settings based on Ethernet that you have to serve if you want to do testing, otherwise you won't get access at this point. The next question is, how do you do your testing? And there is a grouping called Open Alliance. Open stands for one pair Ethernet. Historically speaking, this comes from a situation where the Automotive Ethernet is a two-wire connection, different from the workplace Ethernet with 8 lines 4x2. The Automotive Ethernet is only a two-pair solution, one pair Ethernet. That's where the name comes from. And this Open Alliance Special Interest Group has set as its target to promote Automotive Ethernet and define it rather broadly, anchor it, and take it to the automotive world. It works in so-called technical commissions, TCs. There are quite many of them. I won't run through all of them, but the clear target is that Automotive Ethernet as a topic on the whole is supposed to be described with test documents and qualification documents, so that altogether it will be broadly and widely received in the automotive environment. Originally for 100 Mbit networks, but it's going to be expanded to 1000 Mbit per second networks. For our community, what is of utmost interest is the topic of TC8, Technical Commission 8, which deals with the test specification for Automotive Ethernet ECUs. And we are going to take a closer look at that now. TC8 works on collecting requirements which are incurred in this environment, to also define specifications, test specifications, and then to define test processes and audit processes, so that the testing of Automotive Ethernet ECUs will be fully described. This is our goal, our target, and we've heard several times over today that early testing is better. Then you can see the false beta. That was part of the first presentation, agility presentation, but also in other presentations. We quite agree on that. We want to make an offering where, as early in the development phase, in an ideal case, you do continuous testing, as mentioned several times before, where you can test then Automotive Ethernet components accordingly. And in this context, let's take a look at the software for Ethernet. Those are the ISO OSI layer models there for Automotive Ethernet software. The test spec has to have the target, and it did implement that target, that all 7 layers are to be described. It's organized for that purpose in so-called test scopes, the first one being Automotive Ethernet, and it serves the 2 basic layers, the genuine physical layer and also the data link layer. The second test scope is called TCP IP protocol family that serves network and transport, and the third one serves the protocol layer with some IP, diagnostics over IP or XCP, or also AVB or time-sensitive networking. This somehow is the organization along these lines. If you take a closer look, without elaborating on those more than 800 ISO tests, just for you to get a feel for that, those are the test scopes from the TC8 test spec for Automotive Ethernet. On the physical level, on the physical layer, there are rather few tests, just 20, and data link level, it's another 25 maybe. The main volume of tests is on the higher protocol levels, network, but in particular also transport and application. So altogether, this amounts to more than 800 test cases that have been described, and of course they need to be tested somehow or other. And in order to make that feasible, we do have a proposal, which I want to propose to you next. We've seen it several times before today. Our mighty Troika, Vita Studio, CANoe, and the VT system is suitable then to also conduct the TC8 tests. So the setup is, as you've seen it several times over in the previous presentations, we've got Vita Studio, where tests are designed, where variant handling can be stored, CANoe as the central execution unit for configuration, simulation, analysis, and test automation, and of course the VT system as the interface to the device under test, with the network interface, CAN interface, Ethernet interface, CAN, but also I/O and power supply. And I will take one step back. The target is quite clear, one test system, if ever possible, having just one test system that can serve all layers. I would like to mention one thing, following up on Professor Spillner. We don't have a silver bullet, but a half silver bullet or a silver half bullet. So the attempt is to use one system approach to cover as much as possible. But specifically with regard to physical layer tests, special hardware is required that we don't have in our program on a one-to-one basis. We have to be honest about that. What is our offering in that regard? Let me begin at the top with test design. So with CANoe, with the Ethernet option, we are actually delivering a test studio project where all of the tests have already been implemented. That's basically a target for all layers, layer 1 to 7. That's not fully complete yet. Layer 1 and 7, they take a little bit additional rework, but the remaining layers are out with CANoe 12 more or less completely in the option Ethernet on CANoe 12. All of the essential tests from TC8 as a studio project have already been made available. This is going to be further expanded with the following service packs. It's organized in the same way as the test groups from TC8. So what you can see in the project view are the individual test groups as I showed them to you earlier. So it doesn't fully go without intervention. You have to slightly configure the test, but we try to reduce it to a minimum. So there's basically one global parameter file with which we have to adapt for the test specimen, and then per test group there's one parameter file with which you have to make specific settings, but that was then already it in terms of configuration. The rest is delivered already by the package, and those who are already using Studio, those who have come to know it today, you can expect that the tests are mapped in individual cases as contained in the spec. So they are then carried out by CANoe. CANoe takes over the test execution. I have to add here that as a rule, they cannot be simply connected to the device under test, but the DUT needs functionality to be capable for the testing. At the same time, it's required that in the sequencing environment, CANoe, code is running that interacts with the device under test in order to prepare the test. An example, the address resolution protocol, if you wish to test that, then before that, you have to delete to to clear the address table, and that's a functionality that the execution environment has to offer. And in the DOT and in the ECU, there has to be code taking that action. So in that case, actually clearing the ARP table. The necessary prerequisition has, however, been made on the CANoe side. The DOT has to hold the counterpiece in terms of code that takes that up. And those are so-called stub functions that we also offer in CANoe at this point. What we also offer is a reference DOT, a simulated Ethernet ECU that behaves in an ideal way with which you can counter-check your tests. Before you connect the real device under test or test specimen, you can connect the reference test system to make sure that your tests are running more or less orderly and programmed correctly. So that is on the execution environment on CANoe. And then on to the topic of direct access. What happens from the VT system side? I would like to illustrate it with one example. This is one test from the TC8 test spec, physical layer test, which is called far open. So what's being tested is what happens if at the link away from the test specimen in the test system, if there is a line interruption. And we can then map that with the VT system. In a moment, I'm going to show you how. The test target is that the device under test reacts appropriately if there is a line breakage, so that fault entries are generated, and the test system has to ensure that the test specimen is running, and it will have to coin in the appropriate fault. So what is done for the purpose? First, the feature is triggered. This is exactly the topic, that functionality must be there in the device under test. Then the test system creates an appropriate fault, which is breakage of the line, opening a relay for some time, and then the relay will be closed again, and then the fault will be read out, and as a rule, then the tests are repeated, in that case 100 times, and then some evaluation is made. So in this way or in a similar way, the tests on the physical layer are being set up. Now, let's take a look at what we offer in terms of our VT system. This is a comparatively new model, VT6306 Ethernet interface module. It fulfills several functionalities. For once, it's an Ethernet network interface in order to get access to the Ethernet link in the first place with the taps, as I showed it earlier. On the other hand, it also offers fault injection and also two 100 base TX, 1000 base T standard Ethernet access channels. You can see them. It's a bit difficult. No, you can't see them really. They can only be seen from the inside. 6 automotive Ethernet channels. So they can generate timestamps for Ethernet frames. They can be synchronized, of course, with other network interfaces. So if you've got the issue, for example, that you have to react with a CAN message to something that's happening in the Ethernet network, then they can also be synchronized. What we had earlier, tapping, is being supported. All of the other functionalities that you may already know from network interfaces, they're also included here. So that's the VT module dealing with access to an automotive Ethernet network or link that is made possible there, and electrical faults can also be set up there. What is worth mentioning as well, it's not the only Ethernet interface, but depending on what you need for testing, there is quite a range of automotive Ethernet interfaces. So we continue our development work in that regard, but those are the ones that are viable at the moment and common. In the middle, you've got the VT module on it. That's the only one that offers fault injection, but the other Ethernet interfaces, they've got other characterizations. 5640, for example, has got very many channels, so 12 plus a local digital IOs. Then the smaller devices on the right-hand side, they are also more affordable with fewer channels, but then also less functionality. So this is a very staged step program, but we continue to develop that, especially when it comes to higher band rates, multi-gigabit Ethernet, or even more performance. So we permanently continue the development work along these lines. So that was it for the first part. Let me summarize. what we've heard about the topic of Ethernet. I tried to tell you why Ethernet is important and getting more and more important as a topic. What are the differences to classical bus protocols, also from a testing perspective? What do we have to do in order to reach and test an Ethernet network? And what about the taps? How does that work? And then in the second part, I gave you a gross overview over the TC8 test specifications. How are they set up? What's in there? Which tests are being run? And the third block is what can we at Vector offer? An exemplary TC8 test system. And once again, it's not the silver bullet. It doesn't cover everything 100%, but a comparatively large part of the tests that have been formulated in the TC8 test spec can be run with that and further developed and further processed. So for once, we have got the package implemented in VTest Studio, the test cases as set up by TC8. Then we've got CANoe as the test execution unit with the additional functionalities in order to get the test specimen prepared and to then address the functionalities for the test specimen, and with the opportunity of having a reference test specimen and testing the test, and then interfacing either with the VT system or also with another amount of network interfaces, Ethernet interfaces. And we believe that is already a very good starting point in order to get to begin with automotive Ethernet testing. Some of you may have seen that outside. Maybe the reference comes rather late, but I think shortly after the event there is an opportunity. Those who haven't seen it, in the very remote corner next to the Hill cabinet, you also have an exhibition area showing TC8 and the concrete test up. If you've got additional time, I think our colleague Yuri will be available to explain the matter to you in more detail. That much on automotive Ethernet testing. And as I promised, I would like to conclude by giving some outlook on what we are doing within the VT system beyond Ethernet. What can you expect in the near future? In that regard, I would like to briefly, well, most of you probably know VT system in one way or another. As it is today, you're already using it. I don't want to elaborate on each model. There are roughly 4 blocks of offerings, one of them being an ECU I/O block with the fully featured modules that also allow for fault injection and can respond to all kinds of input situations. Then we've got a block with network interfaces. That's the CAN-LIN network interfaces, including also the 6206, 2710 sensor protocol interface. Then we've got a block with infrastructure devices, backends, casings, power supplies, and a block with rather system modules. In part, they go to the test system. In part, they map test rig infrastructure. And there are no black holes there, but some white spots that we will be filling in the near future. With regard to system, we are making plans for a switch matrix, which allows for complex switches, then for IOs, ECU access. We are talking about the topic of 48-volt networks and also higher currents or higher speeds. When it comes to infrastructure, more PC power altogether, high speed, network channels are always an issue. Image processing keeps coming up. And with regard to network interfaces, quite obviously, gigabit Ethernet is the issue, or further serial buses that we are not yet serving at the moment. So we are approaching quite a few of those elements. The first topic being the switch matrix. It's the development has finished. We are procuring for the series production, will be released in summer. So the motivation is to switch higher currents flexibly. It offers an 8x4 matrix on a module where you can freely switch currents as needed. Additionally, then, you practically each path or gap of the matrix can be equipped with the PWM, so you can not only switch, but you can also make a bouncing contact simulation, for example, on a single block or an individual path. It will be capable of doing 60 volts. That was mentioned several times before today. We face that topic. 48-volt onboard networks require 60-volt capacity for the modules. It will be able to switch with up to 10 kilohertz, which is sufficient for bouncing contact simulation in order to simulate that. And per path, it will be able to switch 16 amps. If the 16 amps are not sufficient, then on account of the technology we use, semiconductor relays, back-to-back switched semiconductor relays, this technology enables the bundling of channels, operating 2 channels in parallel, and then also switching 32 amps, which reduces the matrix, but it increases the opportunities in terms of current. It's realized in such a way in CANoe that for those who already know the VT integration, there's also manual GUI, whereas could expect it, individual nodes can be clicked, and then they will be switched, then the path will be contacted. Well, if 2 paths are in parallel, then they will assume the same color. Otherwise, the individually switched paths are in different colors. Nothing special, but a little bit intuitive, so that you recognize where you're just moving. And apart from that, it's normally integrated into the VT configuration concept as you know it. PWM switching is solved as a bit stream, like on the 2516 module also. Same mechanism, same handling, as I would like to say. Then switch matrix, we believe that it can offer added value for test rig switches. Then we've got a completely different topic, which has got nothing to do with Ethernet, but it's very exciting. Some of you probably know our user FPGA modules. So basically we've got all the modules that are measuring in one way or another. So they're also available with the user FPGA variant. They've got local execution power. So under FPGA, they've got that on the board. And time and again, we are reaching the limits where with the FPGA FI module, only the I/O channels of one module can be served. And in order to enlarge this framework, we have the topic of interboard communication. With that, the user FPGAs in different modules can be connected in a ring. The processor boards, for those who know it, you will know it, that they've got 2 little flat connectors. You can use them to set up a ring, in this example to 4, but it could be more or less. And then accordingly with the FPGA manager, the ring can be configured. So you can select who then is a writing module in the ring being offered there, and who's the recipient. That's how you can configure that. Then the ring has been set up, and then beyond the normal data transport via CANoe or Ethercat, then you can much more quickly exchange data from FPGA to FPGA. To give you a feel for it, if you've got 2 or 3 modules in the ring only, and if you've got less than data, so if you've got a synchronization task, then we are talking about 20 microseconds that one data needs to get around. And that's more than 2 orders of magnitude faster than what we have been able to do so far. For applications that need outputs or have to react to inputs rather quickly asynchronously, or where the data have to be distributed between user FPGAs, this is a very powerful enhancement in order to be able to serve also faster systems. And then we've got the topic of 48 volt onboard network, 60 volt capability. Some of the modules can already do that. The switch matrix module can it. The 2816 is also 60 volt capable. We thought about what else is needed, and we got to the point that at least the 1004, our measurement module, that takes off ECU outputs, and the 7001 that supplies power then will also have to be capable of 60 volts. And this is the offering that we're about to make. There are 2 new modules, 2 variants, one of them being VT1104, the 60 volt variants of the 1004 with same functionality but with solid state relays instead of mechanical relays, and the 7101, the 60 volt variant of the VT7001A, 60 volt capable, and nevertheless covering all the current. For those who don't know the details, 7001A is capable from a few microamps to 100 amps of current, and the 60 volt machine will also be able to perform that. So we need to use a little trick, setting on hybrid relays but that's feasible like that, and it can practically do the things that the 7001 can do, inclusive of the 60-volt capability. Both of them will be coming out in the course of the year, 1004 roughly in summer, 7101. If nothing comes in between, if nothing hinders it, it will come forward in autumn. Then we are working on another module where a prototype already exists that covers the gap, 2808. Current measurement module closes the gap between the current measurement capability of the 7001 and the 2816, so it offers 8 channels with high accuracy. So I won't read everything down. We go from about 1 milliampere to 16 amps on 8 channels independently, then current and voltage. And if the 16 amps are not sufficient, then additionally through a sense access, we can apply additional cabinet voltage. So if you've got higher currents, then you can use a sense access then, and you can then get the current into automation. We believe that this is a meaningful addition to the portfolio that we're having. Technically, it's between the 2816 current measurement range and the 7001 in terms of current measurements. And finally, we are thinking about a PC module next generation. At the moment, we've got 2 PC modules in the VT systems. We will follow up there in terms of computing power with a strong computer, but in terms of connectivity with more Ethernet, not automotive Ethernet, but standard Ethernet accesses in order to get test connectivity or connection of LXI devices, for example. That was a little tour of what we intend to do with regard to the VT system. What remains to me is say thank you. I hope you can take some information home with you on the 2-topic Automotive Ethernet networks with TC8, what can Vector offer you, and also on the enhanced topic about what the VT system will bring forward and will produce in the next future. Thanks for the attention.